Hello and welcome. We are going to talk about the life and death of stars. This is going to be a two-part series because there's kind of a lot to go over and I don't want to make it kind of overwhelming and too long. So this week in part one, we're just going to kind of talk about an introduction and we're going to get very familiar with something that we call the HR diagram. I hope you guys are ready. So obviously humanity has been looking up at the stars forever, as long as we've been around. But what's the history of actually examining stars as kind of astronomical bodies? And kind of tied into that is knowing that the sun is a star, right? Because the sun is what really helps us to understand other stars. And so knowing that the sun is a star kind of helps us to examine other stars that are very far away from us. So there's not exactly like a aha eureka moment in science where they're like, oh, the sun is a star. But the idea was actually first proposed, that we know of, back in about 450 BC by a Greek philosopher called Anaxagoras. So he basically proposed that the sun was a fiery stone and that the other stars were just farther away fiery stones, and that the sun was very large and looked small because, it was somewhat distant from us. Which, is surprisingly good for 450 BC. This actually always makes me think of the scene in The Lion King where they're all lying around talking about what they think the stars are, and they're like, oh, it's, the spirits of the departed or whatever, and then Pumbaa's like, I think they're great balls of burning gas that are millions of miles away. And they all laugh at him because it sounds ridiculous, but So basically this idea did seem pretty ridiculous to people for a long time, especially because the stars were often considered to have religious importance, and so kind of treating them as, just like the sun or as scientific objects was kind of frowned upon, shall we say. For example, Giordano Bruno, back in the 16th century, proposed that not only was the sun a star, but that all of the other stars were just like the sun and could have planets of their own, which was really crazy at the time. In fact, it was so crazy that Bruno got burned alive for heresy in the year 1600 for this and other reasons. But yeah, this idea was very challenging to basically the thinking for a very long time because it kind of upended some power structures that existed in relation to the church and to religion and to just how humans viewed their place in the universe, i.e. that we were special and not that the sun was just another one of these dots of light that we see so many of in the sky. But you can't burn everyone alive for heresy, thank goodness for me. But so this idea kind of continued to float around. So there was a Dutch scientist in the 17th century called Christian Huygens. I'm sorry, I'm so bad at pronouncing names. And he looked at the star Sirius, which is one of the brightest stars in the sky, and he calculated how far away Sirius would be if Sirius was just a star like the sun. So if the sun and Sirius were the same, based on how bright Sirius looks to us, how far away would it be? And he found that the distance was, absurdly large. And so it was kind of like, is this real? Is this possible? Can things be this far away? And of course, we know that Sirius is actually much brighter than the sun. And so the distance he calculated was actually not even far enough away, but it was still pretty far. So finally we get to the 19th century. And by this point, the idea was pretty well accepted that the sun was a star, but it wasn't really considered proven. And this brings us to Friedrich Bessel, aka he of the Bessel functions. If you're a math fan, you may have heard of Bessel functions, but he also was an astronomer. And Bessel was the first one to measure distances to stars directly without having to rely on assumptions about what the stars were like. For example, like Huygens did with Sirius, assuming it was like the sun. So he used a method called the parallax method, which is just basically looking at how the apparent position of a star changes as the Earth moves around the sun to kind of tell how far away that object is from you. Closer stars will appear to move more relative to the background than farther away stars. So I've talked briefly about parallax in videos before, so I'm not going to go into too much detail, but the kind of analogy that I like to use is if you think about holding your thumb out in ahead of you and against some background, and you open your right eye and left eye and turn, you'll see that the apparent position of your thumb relative to the background changes, and that's due to the parallax between your two eyes. So basically you can think of this eye as the Earth on one side of the sun, and this eye as the Earth on the other side of the sun, and looking at a star, which is your thumb, relative to a background, which is just further away stars, basically. And so then that can give you a measurement of the distance. So Bessel did this in 1838, and this was considered kind of proof that in fact the sun was a star, because the distance that he found to these stars was consistent with what we would expect if these other stars were like the sun. For example, like Huygens calculated that they would have to be very far away. So this was proof that they were in fact very far away. Okay, so by the 19th century, we were absolutely sure that the sun was a star. And that's great because the sun is right next door, you know, astronomically speaking, it's only 8 light minutes away. And so we can study the sun in a lot of detail. But the sun is only one star. Stars have a huge range of characteristics and varieties. And so by just studying the sun, we're really only getting one particular kind of star. And in fact, it's even worse than that, because not only are we only seeing one particular type of star, but we're only seeing one particular point in the life of the sun. Because the lifetimes involved in astronomical objects are so long that even the entirety of human history is just a blink of the eye compared to it. So we're really only getting a one snapshot in time of one single star. And that makes it really hard to infer what's actually happening. How did the sun form? What did it look like when it was young? What's it going to look like as it dies? As a side note, we use a lot of anthropomorphic language when talking about these stars, but just remember that stars are not alive, they don't feel, none of this hurts them. Thanks. And so this is a really difficult problem, because even so-called short-lived stars actually live for millions of years, which again, longer than the entire human race has been around. So we really can't watch any single object from death to birth to death. That would make more sense. We can't follow a single star and say, okay, here is it when it was young, here is it as it was middle-aged, here is it dying. We just can't do that. We don't have the time. But astronomers have a pretty good idea of what is happening in stars. Not perfect, because science, but we have a pretty good idea. So how do we do this? Well, the answer is by looking at a lot of different stars. Imagine that you were an alien observer trying to learn as much as you could about humans, but you could only take kind of one snapshot of Earth at any given point in time. And so you took a picture and you kind of tried to categorize humans in certain ways. And you would see that there were a lot of humans that are kind of in their middle age, that have, you know, say 2 legs and 2 arms, etc., etc. And you'd see that there are a few humans that are very small and a few humans that are very big. And this kind of helps you figure out what's typical for humans and also what they go through without their lifetime, because you can see these small ones and you can kind of infer that they grow into the bigger ones, and you can kind of infer the relative time scales, right? Because you're seeing a certain number of ones in a certain stage, and so that kind of tells you how long this stage might last. And of course, every single human is different. So this kind of population level study is difficult to do because you're trying to draw out general information from just specific wide variety of objects. And so we do the same thing with stars. Stars are all different. They have different masses, they have different ages, they have different metallicities or compositions. They are born in different places within the galaxy. So basically, astronomers have to look at all of these very unique and different kind of stars, observe the general trends, and try and tease information out about what's actually happening to a given star. And so it's like detective work. And it's really a balance between observations and theories, because the observation is that snapshot, right, that you're taking, that data that you're getting about the stars. But to really understand it, you have to know the theoretical underpinnings, and you have to be able to, for example, recreate what you're seeing in observations with our understanding of what's happening. And so theoretical models try and match the observations, try and explain the observations. Observations, discover new things that help us understand the theory and give us more constraints on our theories. So this is a very give and take between observational and theoretical astronomy and astrophysics. Okay, and that is all kind of the background that's bringing us up to the thing that we're really going to talk about today, and that is the HR diagram. So when astronomers hear HR, they don't think human resources, they think Hertzsprung-Russell. So an HR diagram is named after 2 astronomers that actually discovered it or created it independently in the early 20th century, Hertzsprung and Russell. And this was originally an empirical tool. So empirical means something that we learn from observations, so i.e. not theoretical. But now we actually use the HR diagram both as a theoretical and an observational tool, but it was created as an empirical tool to kind of look at stars as a whole. So in the next video, we're going to talk more about the actual life and death of stars, and I'll be referencing the HR diagram quite a lot. And so I want you to be comfortable with what I'm talking about when I talk about the HR diagram, and it can be a little bit complicated to understand. So bear with me. Hopefully that you won't consider this too painstaking detail or anything like that. If you're already familiar with HR diagrams, you can just skip right to part 2. But for those of us that want to learn more about the HR diagram, let's dive in. Okay, so first let's talk about the x-axis, i.e. the horizontal axis. For an observationally based HR diagram, this is usually going to be color. Now, astronomers tend to quantify color by something called a color index. So basically, you look at a star between 2 different filters, and then you subtract the star's brightness between the 2 filters, and each filter is kind of looking at a certain wavelength. And so the difference between them kind of tells you the relative strength of one wavelength to another, and the wavelength of light is what gives something its color. So this is called a color index. There are various filters that you might see used for this, so I'm not going to get into the details. A very common one, for example, is B-V, but you don't really need to worry about that. I'm just telling you it's color, and we do have a way of actually quantifying this. It's not just a qualitative measurement. And with color, you'll find that bluer is to the left and redder is to the right. Bluer, redder, bluer, redder. Okay, but theorists don't usually use color for their HR diagrams. They use temperature, or what's called the effective temperature of a star. Now the effective temperature is strongly related to the color, but it's not exactly the same, so it's not like a one-to-one, but there is a way to kind of convert between one and the other, and they are kind of showing a very similar quality of the star. So that's why we use both of them, and color is, more easily observed, whereas effective temperature kind of comes out of your theoretical model. So temperature and color are the 2 most commonly used x-axes. Now for temperature, in order to make it kind of the same as the color axes for better comparison, I want to note that hotter temperatures are on the left and cooler temperatures are on the right, which is a little bit backwards of how you would think of a typical x-axis, right? Usually you think as the x-axis goes, it gets larger. But in this case, the temperature actually decreases as you go to the right. And that's because hotter is bluer and cooler is redder. And so to kind of keep these comparable, we use the kind of backwards temperature scale. And then just a last note that the color is usually, like I said, just a relative magnitude, so it's unitless. And the temperature unit is Kelvin, which is basically Celsius, but without any negative numbers. Okay, so what about the y-axis? So the y-axis is the vertical axis. Now again, this is going to be slightly different. There are different ways of showing kind of similar information. So for an observationally based HR diagram, the y-axis is usually going to be magnitude, and it can be either apparent magnitude or absolute magnitude. So the apparent magnitude is exactly what it sounds like. It's the apparent magnitude that we see when we look at the star. It's just what we measure for the magnitude. Whereas the absolute magnitude is what the magnitude of the star actually is at a given reference. And this is going to be different than the apparent magnitude because as you get farther away from an object, it appears dimmer to you. There can also be dimming effects from dust that might be in the way and things like that. So the absolute magnitude is a property of the star, but the apparent magnitude is a property of both the star's absolute magnitude as well as the distance and other factors. Primarily distance is the one that we most really worry about, but there are other factors. So like I said with the x-axis, magnitude is a unitless quantity. And it's a kind of confusing quantity for a lot of people because it's a very it's a quantity that has a lot of history and it's been used for a long time in astronomy, which means that it's not 100% logical for the way we might think of it today. So one key note about magnitudes is that lower magnitudes are brighter. So something that has a magnitude of 1 is about 100 times brighter than something that has a magnitude of 6. Because magnitude is not a linear scale, it's like roughly a logarithmic scale. So magnitude, lower is brighter, and you can have negative magnitudes. Now historically magnitudes were referenced to the star Vega, but that's not how we do it anymore, but basically you can kind of think of the star Vega as generally being 0 magnitude and then things either brighter or less bright than Vega. And so then on the HR diagram, the brighter objects are going to be higher up and the dimmer objects are going to be lower, which means that magnitude is going to be lower as you go up and higher as you go down. We do like to make things confusing. Now, if you're looking at a theoretically based HR diagram, it's probably going to use luminosity. Luminosity. Why does my O sound so weird? My Midwest is really coming out there. Luminosity. Anyway, luminosity. So basically luminosity, you can kind of think of it as being comparable to the absolute magnitude, and that it is an intrinsic property of the star. And so the star has the same luminosity regardless of how far away we're observing it, how much reddening there is, anything like that. So it's a property of the star. So like magnitude, luminosity is measuring how bright the star is. In this case, it's a energy per time that the star is releasing. And so the SI units for that would be joules per second or watts. So this is a power, right? This is the power that the star is emitting. But those units don't really make a lot of sense for astronomical purposes, so you'll usually see it in terms of what we call a solar luminosity, which is basically just the luminosity of the sun. We use that, that's one solar luminosity, so then we kind of scale everything to how luminous the sun is, which happens to be 3.83 times 10 to the 26 watts, I believe. So you can see why that's not very convenient to use. So we kind of bundle that up into this solar luminosity. You also frequently see that this luminosity axis will be logarithmic, but don't really worry about that too much. And again, it's going to be kind of similar to the color magnitude HR diagram, and that brighter objects are going to be higher up. So in that case, they have a higher luminosity, and dimmer objects are going to be lower down. In that case, they have a lower luminosity. So that's kind of not backwards, as opposed to magnitude, which seems a little bit backwards. But okay, so those are the typical axes on an HR diagram. So sometimes you'll hear an HR diagram called a color magnitude diagram, if it's one of these ones that uses color and magnitude on the axes. You might hear it called a temperature luminosity diagram, but probably not. That's not a very commonly used term. And yeah, but those are all HR diagrams. Okay, this has been quite a lot of words, so let's take a look at some examples to help you get a better idea of the HR diagram. Okay, so here is an HR diagram plotting all of the stars from a Messier object called M55. Now take a look at the axes that we just spent a long time talking about. Note that this helpfully has actually both types of axes on it. Color labeled on the bottom x-axis and temperature labeled on the top x-axis. And then it has luminosity labeled on the right y-axis and magnitude labeled on the left y-axis. So you can kind of see how both of these things can be used. Note also that in this one, the points are color-coded along with the x-axis, the color, in order to kind of help you visualize the color. And so you can see bluer, redder. So like I said, this is an HR diagram of the M55 cluster. So this is an empirical observational HR diagram. So even though it's just basically looking at a bunch of stars and throwing it into this parameter space and seeing what you actually get something that has quite a lot of structure to it. So this tells us that somehow these colors and magnitudes or the temperature and luminosities are related. And that it's not just random, right? If the dots were just kind of randomly spread without this diagram, then it wouldn't be very helpful. But it is not. Because it has structure, it can tell us something about the stars. And because this is for a single cluster, we expect the stars to be pretty similar, and in that they are probably pretty much the same age, and they have similar compositions because they formed out of the same kind of material. So they're going to have the same kind of metallicity. So really the only difference here is kind of the mass, basically, you can think of it. Okay, so maybe the structure is only there because it's a cluster. So what happens if we look at a much larger group of stars that are maybe unrelated? So this is an HR diagram of all of the stars observed by the Hipparcos mission. Now this was a scientific satellite that was launched by ESA in the 90s, and it observed over 2.5 million stars. So it got quite a lot of data to fill out this HR diagram. And in this case, the color is not showing the value from the x-axis. The color is actually showing the density of points because there's so many points on this plot that they would just all be overlaid on each other. So the kind of redder areas are more densely populated with points. So even though these stars are vastly different in age, location, composition, there's still a very clear structure in this HR diagram. So basically the existence of this structure is what makes the HR diagram such a helpful and useful tool. Okay, so this HR diagram shows you kind of some of the main groups that we identify, some of the structure that we identify in an HR diagram. Also note that here we see yet another way to label the x-axis, just to confuse you. Here they're using spectral class, which is related to the temperature and mass of a star. That was developed over the years, originally based on the strength of the hydrogen lines in the spectra. Again, I don't want to go into all these details, but spectral class is a way that you can categorize these this axis. Also note that the spectral classes are not in alphabetical order. Again, this is because they were originally developed based on the hydrogen lines, and then we kind of learned later that there was actually, you know, a more physically defining classification underlying that. And so we reshuffled them. And so the new order now, the order that we use is OBAFGKM. And astronomers like to remember this by Oh Be a Fine Gal Kiss Me, or Oh Be a Fine Guy Kiss Me, whatever your preferences is. So this big swath that kind of runs diagonally across the HR diagram is what we call the main sequence. And it's the main sequence because this is where most of the stars are located. If we go back to the Hipparcos one, you'll see, right, look at the density of points along that main sequence. That's where the majority of stars are on the main sequence. And this is because this is where stars spend the majority of their lifetime. So when we're looking at a bunch of stars, they're most likely going to be in this stage of life. Just like if you were looking at all the humans on Earth, they would most likely be kind of, not children, not very elderly, they would be just adults. Our sun is a main sequence star. It is a G-class star, and so you would see it would fall right here in this kind of yellow area of the main sequence, which the sun is pretty yellow, so that makes sense. So these other groups that are identified on here are what we call evolved stars, and that they've evolved off of the main sequence. So you can think of these as kind of stars in the twilight of their life. In this case, they've labeled out giants, supergiants, and white dwarfs, but I'm not going to get into the details because we're going to talk about all of that in the next video. Okay, so by gathering information about a lot of different stars, we can kind of piece together the story of what is actually happening as a star is born, lives, and dies. Using tools like the HR diagram, we can categorize these stars empirically and then go back and build the theory behind it that helps us understand why this sort of structure or empirical categorization is happening. And so then from our theoretical understanding of the physics, we hope to recreate, basically in theoretical manner, the observations that we see. So in the next video, we'll actually go through the life and death of a typical star, but for this video, I hope you learned a little bit of the background of how we study stars and stellar evolution and the HR diagram, which is a really awesome tool that's used by astronomers to study stars. Thanks so much for watching, and I hope you will come back again soon. Have a good one. Bye.